Let's continue with one of my favorite statistics books. This is Mathematical Statistics by Knight. Let's see what it covers. It has Introduction to Probability, Random Vectors, so that's all like the first three chapters, all like classical probability. Then we come to Principle of Point Estimation, Likelihood-based estimation, optimality in estimation, interval estimation, linear and generalized linear models, and goodness of fit. Yeah, I like this book because I think it goes a bit more in depth than the usual statistics book. Like, I mean, statistics books are of various kinds, right? Like you have books going really in depth in math, all extremely rigorous math. I typically don't like those. I don't think statistics books should have too many rigorous math where you talk about measures and dominated convergence theorem. Then there are books like this one, which are still quite in depth and offer proofs and derivations. I think this book is an excellent example of this. Then there are books which are very practical, and I typically don't like these books, even though I do see their value. I think practical books are necessary if you want to be a good statistician. You can't only trust on theory books. You need to, look at the wisdom of what all statisticians did, kind of, and how they approach things. Because statistics is not math, right? Statistics is not a part of math, and that's not meant as an insult. It's meant as a compliment. Statistics means you need a kind of deeper intuition. You need a statistician's intuition for things, which cannot always be rigorized. Like you have some data and you see some trends in your data. What are you gonna do next? You can't rigorize that. You can't put that in theorems. You can't put that in rules. You need some kind of intuition. You need a very deep understanding of your data analysis and of the field you're treating. So that can be very tricky. And this is why the very non-rigorous books can also be useful because they tell you how to approach things and they refine their intuition. While a book like Knight, which I really do like, is not going to tell you how to analyze a specific data set. It's not going to tell you that. A book like Knight is good for a mathematician, and that's why I like it. But it can't be the only kind of book you do for statistics. So yeah, this is Knight, very good book, highly recommended. Next we come to another book I like, Div, Grad, Curl, and All That by Shea. It's one of the most famous texts on the topic of vector calculus. It starts with vector function electrostatics, so it's very related to physics. They really explain they really use physics to explain div, grad, and curl. So you have surface integrals and divergence. Then you have line integrals and the curl, and finally the gradient. I like this book. It's really a book for physicists, right? It's a book that really shows the physics and the intuition behind the concepts. The math is done nicely, not hyper rigorously, but still pretty nicely. Mostly in an intuitive way, but not brain dead unintuitive. So yeah, very good for seeing the intuition of things. Now I need to say that I like this book, and if somebody is willing to work through it, I'm definitely willing to. But I never recommend it because I think there are physics books. I'm thinking, for example, of Purcell Electricity and Magnetism book, which kind of already do these kind of things, and actually do them better in a sense. So yeah, I think if you want a specific book on div, grad, and curl and vector calculus, this is really a text you should get. But I think most physics books already kind of do this in their physics texts, and well, not most. Like if you're doing Griffiths, right? Griffiths electromagnetism, Griffith is, I think, a notoriously unintuitive book. It just gives the physical, it just gives the mathematical proofs, no, the mathematical way of dealing with things, just the definitions and how to handle it, but it doesn't tell you what they mean. But the books I like, which is, for example, Purcell, do tell you this kind of things. And that's why then you won't need some book like this. If you're doing Griffiths or the very standard, very unintuitive kind of books, then you really do need this. Next, we come to Florian Scheck, Statistical Theory of Heat, which is a book on statistical mechanics. So it starts with basic notion of the theory of heat, thermodynamics, classical framework, geometric aspects of thermodynamics, probability, state statistics, mixed phases, transition, stability of measure. So yeah, a book on statistical mechanics. I think I have all of Scheck's books, but I honestly don't really like them that much. I think they're kind of unstructured. I think they're kind of all over the place. I think yeah, they're not bad. I think there are many jumps in this book. I just really don't like reading them for some reason. Maybe because they're grad books and I'm maybe not at that level yet. Maybe, I don't know. Here comes two books, Mathematica for Theoretical Physics. The first book is on classical mechanics and nonlinear dynamics, and the second book is on electrodynamics, quantum mechanics, general relativity, and fractals. Yeah, so it's very much a computational book of computational physics. So it does things like classical mechanics, where it does mathematical tools, Newtonian mechanics, kinematics, central forces, calculus of variations, Lagrange dynamics, Hamiltonian dynamics, chaotic systems, rigid body. Then we come to nonlinear dynamics. And then in volume 2, it covers electrodynamics, quantum mechanics, and general relativity. And then at the end, it studies fractals. So yeah, very much a book on how to compute stuff. If you're into computational physics, highly recommended. Even though I do think there are better books on the topic, I guess. But this is not bad. It really tells you how to compute certain stuff. The only problem, I guess, is that I don't personally like Mathematica very much. So yeah, that's a bit of a problem since the book is quite heavily using that. Okay, then we come to a rather old book, An Introduction to the Theory of Relativity by Rosser. You can see how old this book is. This book is part of the library since 1965. And until they, I guess, decided to throw it away, and I got it. So yeah, it starts off with a historical introduction to Newtonian mechanics, then the theories of the ether, and all of the experiments are really worked out in depth. Like they spend like 30 pages on all of these things. Lorentz electron theory, so Lorentz transformations are next. Then we have relativistic kinematics, relativistic optics even, relativistic mechanics. Then we have general geometrical representation of the Lorentz transformation and the use of four vectors. Electromagnetism as a second order effect. This is something I rarely see in books, actually. The relativistic transformation of Maxwell's equations. The relativistic transformation of the potentials. Development of the theory of electromagnetism using four vectors and tensors. A critique of the theory of special relativity and the clock paradox. And then we come to the general theory of general relativity at the end. So yeah, I think, yeah, it's bad. You definitely won't find this in a new book, especially the extensive discussion of the ether and of the ether theories makes this book already special. Usual book, like the usual books nowadays, mention the ether and kind of explain what it is, but they don't really go very deep in it. The Also, the links with electromagnetism here that this book makes is rather special. Yeah, I do think it's a gem though. It's definitely an old kind of book, and I like I understand people who want modern stuff, like a modern treatise, but something about these old books and these old kind of knowledges really speaks to me a lot, and really makes me very interested in these kind of things, like the old ways of seeing things. I think sometimes it makes a lot of sense seeing things this way, and not, for example, new modern ways with all their fancy tools, fancy mathematics, and nice group theory and stuff. I like it. Obviously, I'm a mathematician, of course I like it, but the old ways is often more elegant in my point of view. So yeah, somebody ever wants to do this book, I am very much open to do it. But yeah, I don't think I would recommend it to anybody though, because I think I'm kind of alone with my taste in these kind of niche old books. Here we have Information, Physics and Computation by Mézard and Montanari. So it starts with information theory, statistical probability physics and probability theory, introduction to combinatorial optimization, SCRIM, do you see this? A probabilistic toolbox. Then we come to independence, number partitioning, introduction to replica theory, vector graphs and graph ensembles, low density parity check codes, spin glasses, bridges, inferences, and Monte Carlo methods, belief propagation, decoding with belief propagation, the assignment problem, Ising models on random graphs, linear equations with Boolean variables, the IR1RSB cavity method, random case satisfiability, Galaxy states encoding theory, and ongoing story. I definitely never worked with this book, so I have no idea what it is about really. It looks good, I guess. I don't really think it's my cup of tea though. Krim might be interested in this, but on the other hand, it's physics, so probably not. The last book of today is a statistics book, but one I really like, and it's a very heavy book. Look at this brick. It is one I really like. It's Niederkuttner, Nachtsheim, Wassermann, Applied Linear Statistical Models. So this is a book on regression, on linear models, regression, all kind of things, and it really, really does it justice. The table of contents is like massive, so I'm gonna go over it completely. So it's simple linear regression first, and we have multiple linear regression where there are multiple covariates. Then we have nonlinear regression, analysis of variance, and all kind of. It's really comprehensive, and I really like it because it satisfies my urge of doing derivations. Though the derivations are not too mathematical, the derivations are not too rigorous, but I think they're convincing. And that's what I like in statistics. I like a convincing derivation, not a rigorous one. But it also shows a lot of examples, a lot of ways where things can go wrong. The questions, the problems are also very nice. A lot of practical problems where you have to work with your own data set and do things and derive things. Like here we see here, they ask really some questions about about analyzing some data set, and they really ask very in-depth questions. Not mathematically in-depth, but really they really try to enhance your understanding a lot. So yeah, I really like this book. I think it's an excellent book for somebody who is quantitatively gifted or knowledgeable, but who still wants to do things in practice and really wants to see things how they are in practice and not in some theoretical world, ivory tower world. So yes, I like this book. Very highly recommend to anybody into statistics.